Let's take a look at the images formed by concave or diverging lenses. I've drawn out a diverging lens with the same focal distance that we used in the introduction. So we've got a focal length of 3 centimeters. In this case, I've already noted the focal points, one on either side of the lens. I've also now drawn an object for us to consider to trace out through ray tracing and through calculation what the resulting image will be, where it will be, its orientation, and its size. The initial size is noted here as 2 centimeters in height, and we're using a tree. We again could consider this to be the appropriate scale, or we could say it's a representative scale, so 1 meter is equal to 1 centimeter, so we're really talking about a 2-meter tree. But of course that would make for an absurdly large lens, so let's stick to maybe a very tiny tree. So how do we do this? Well, let's do some ray tracing. What are some representative light rays we could use to trace out where the image is formed? The first ray that I think would be useful is going to be starting from the top of the object and going straight to the lens, parallel to the optical axis. In this case, we know from our analysis before that we're going to end up with a ray that is diverging away from the optical axis, such that if you were to trace it back, it would pass through the focal point on the left side. Next, let's consider a ray that goes straight through the center, because we know that a ray going straight through the center of the lens will not change its trajectory, making it a very easy ray tracing example. Okay, last, let's consider a ray that is passing from the top of the object to the lens and then resulting in a ray that's refracted parallel to the optical axis. The way we find that is to go from the top of the object and imagine that it goes without the lens being there to the focal point on the opposite side of the lens. Again, I'm taking these rays as best I can to the center. Okay, this is our thin lens approximation method. And then after it refracts, that ray will go parallel to the optical axis. Okay, so the way that we find the image is going to be, let's trace back these diverging rays onto the left side. So we'll go from the top here, the top ray, and we know that that's going to trace back through the focal point on the left side. Next, I'm going to trace back that second from the top ray that is parallel to the optical axis. And what we notice, hopefully, is that there becomes a point of convergence here, where we have all three of these rays, the two that we trace back and the one that, well, we could trace back but goes along the same line going through the center of the lens. And so that point is giving us the location of our image. Okay, so we have a location of the image and we have an orientation, which is upwards. So let's take our original object and see where its image is going to be. It's going to be right there. It's going to be much closer to the lens, upright, and it's going to be much smaller. Quite a bit smaller. Okay, so that's pretty good. So we zoom back out and look at this in context. Now we know where the image is, the orientation, and the size. We could measure it if we wanted to, and if we've done a very careful job, then we'll get a height of about 0.6 centimeters versus the original height of 2 centimeters. But let's do the calculation and see how it works out. As before, we're going to use the thin lens equation. The thin lens equation is 1 over s plus 1 over s primed is equal to 1 over f. And move this down just a little bit. I also want to write here where my distances are for my objects. So this is going to be my distance to my original object, and that's s. And so in our case, we could measure, and this turns out to be 7 centimeters. We can also note our distance to the image, and we'll denote that as s primed. And we've already noted the focal length of 3 centimeters. Okay. And so this is the thin lens equation. Maybe I'll drop this down just a little bit more. All right, so if we want to apply this, we can isolate for s primed. So we've got s prime is equal to sf divided by s minus f. Now, there's something very important that you must take careful note of when applying this equation for a diverging lens. The f value is going to be negative for the diverging case. Now that is very important. Do not forget. And really that is overall it's a matter of convention, but it's important and it's necessary to work out for this to be applied to the diverging case, where we've got this formation of an image on the same side as the object. Okay, so we know our values, so let's plug them in and get a value for our s primed. So we have an s of 7 centimeters, a focal length of 3 centimeters, and so then we have, but it's negative 3 centimeters, and then we have, don't forget, 7 centimeters minus, and I don't want to forget, so I'm going to put it in brackets again, minus 3. Okay? Just to be really clear about that minus sign. Otherwise, you get into trouble. So here, and I'm just going to add another step just to be super clear. We have on top here minus 21 centimeters squared. And then 7 minus 3. So we have 7 plus 3, so that's over 10 centimeters. So we end up with a value of negative 2.1 centimeters for our location of that. And so we go back up. Does that make sense? Well, if this full distance here is 7, this distance 2, yeah, that looks about right. And I'm just going to measure it. And that looks actually really good. That actually looks really good. Okay, so now let's go on to calculate the magnification factor and then the height of the object. Height of the image. Okay, so the magnification factor is equal to negative S prime over S. And so in this case, we have negative 2.1, and then we have an S of 7. And so we have a magnification factor. I'm just going to put it below. So we have a magnification factor of 0.3. And before I move on, I'm just going to look. Does it look about 30% of the original size? Yeah, that seemed about right to me. Okay. So then I'm going to do H prime because I want to know the height. And that's the absolute value of my M value, which is positive in this case because we have an upright image and the original height. So 0.3 times the original height, which was 2 centimeters. So the H prime, the height of the image, is going to be 0.6 centimeters. And if I actually go and measure in like the full scale view here, 0.6 centimeters is almost exactly right. So if you're very careful in doing ray tracing, you can get very good answers. Sometimes in the textbook or even a test, you can be given a choice. Do this through ray tracing or calculation. Generally, it's much faster to do the math. Much faster. Ray tracing is really great for convincing yourself of these physical relationships and really great to see the math happening through geometry. However, it is a long process to actually do it and to do it really carefully so that the values you end up with are accurate. But that's how we do our ray tracing and calculation for images using a concave or diverging lens.